This is module 10.6, using K to calculate equilibrium concentrations. We're going to start with some easy problems and then work on up to ICE tables. Dinitrogen tetroxide in its liquid state was used as one of the fuels on the lunar lander for the NASA Apollo mission. In the gas phase, it decomposes to gaseous nitrogen dioxide as shown, and it's in equilibrium. Gaseous N2O4 was placed in a flask and allowed to equilibrate at a constant temperature where Kp equals 0.133 atmospheres. At equilibrium, the pressure of N2O4 was found to be 2.71 atmospheres. Calculate the equilibrium pressure of NO2. So the first thing we're going to do is we're going to write the equilibrium expression, and we're going to remember that we're dealing with partial pressures. So we'll make sure that we use partial pressures in our notation. So we have the partial pressure of NO2 squared over the partial pressure of N2O4. And then we substitute in what we know. We are told that K is 0.133, and that is going to be equal to the square of PNO2 over 2.71, and from that you should be able to calculate that PNO2, the partial pressure of NO2, is 0.600 atmospheres. So easy peasy, you know, K, you know one of the values, you substitute in. But what happens if we don't know two of the values? Well, that brings us to Rice tables. All right, so Rice tables with equilibrium constants. There's two types. We're going to start with the easier one. Type 1, consider the reaction of hydrogen with iodine to form HI, and we're given a value of K being 55.64. So a 0.5 liter flask is charged with 1 mole each of H2 and I2. Find the equilibrium concentrations of H2 and I2. Well, the first thing I hone in on is, oh boy, I got a 5 liter flask, so I'm going to have to figure out my molarity. So my molarity of H2 is going to be 1 mole over 0.5 liter, which is, that's an L, is 2.00 molar, which is the same thing as the concentration of the I2. So let's go ahead and get those in, because remember on these we always need to use either concentration or partial pressure. So I'm going to put brackets around there to remind you that we're dealing with concentrations. So we start with 2.00 of each of the pure elements, and we have no HI initially. We know we're going to start making some HI because this is an equilibrium, which means we're going to add 2x. How do I know it's 2x? Because there's a 2 here. I'm going to lose minus x, and I'm going to lose minus x. How do I know it's minus 1x? Because there is an implied 1 in front of the hydrogen and the iodine. Now I fill this in for the equilibrium. I have 2 minus x. I'm going to keep the OOs out of there just to keep things really simple in the table, but I will remember when we go back to do 2 sig figs or significant figures. Okay, so now I've got my equilibrium pressures. I know that Kc is equal to Hi squared over hydrogen concentration times the iodine concentration. And I'm going to put that this is 2x squared over 2.00 minus x squared. Now, this might look scary, but notice that the numerator and the denominator are both squared. So what we're going to do is we're going to take the square root of both sides. So we have our value of K is 55.64. So we're going to take the square root of 55.64 is going to be equal to 2x over 2.00 minus x. So I just came back here and took the square root of the numerator and the denominator. That's fair. Now solve for x. Oh, it's your favorite, algebra. Okay, so we're going to solve for x, and we end up with 7.45. That's the square root of 55.64 is equal to 2x over 2 minus x. And when we go to solve, we'll find that x is equal to 1.58. Okay, at this point, students tend to dance up and down. And they go, oh, I solved for x, I solved for x. That's the hard part, I'm done. No, you're not finished yet, okay? You're not done yet. You need to apply x. So we're going to take a look at the concentration of H2, which is the same as the concentration of I2. And that is equal to 2.00 molar. I'm putting back my trailing zeros. And now it's going to be minus 1.58 because that's my x. So this is 0.42 molar. Put a little box around it. We still have to do the concentration of HI. The concentration of HI is equal to 2x, which is equal to 2 times 1.58, and that is 3.16 molar. So here are your values. Now, at this point, what I would recommend that you do is to take those values, plug them back in to your value for Kc to make sure that you get 55.64 back again. So let's take a look at what we did here. First of all, we made sure that we checked the size of the flask and we converted everything to molarity. Then we recognized when we got to right here that we could take the square of both the numerator and the denominator. So what looked like a messy problem was not a messy problem. Okay, now we're going to do a messy one. So here we go. Type 2, a quadratic equation is involved. Okay, so let's consider the reaction of nitrogen plus oxygen in equilibrium with nitrogen monoxide, and we're given a value for K of 1 times 10 to the negative 5th. A 1 liter flask, thank you, I don't have to convert to molarities, is initially charged with 0.80 moles per liter of nitrogen and 0.20 moles per liter of oxygen. Find all the equilibrium concentrations. Okay, let's write in what we have. We have 0.80. We have 0.20. We don't have any of the nitrogen monoxide yet. Now, we know we're going to start making the nitrogen monoxide, and since there's a 2 right here, it's going to be plus 2x minus x minus x. Now we're going to figure out what we have in our table. We have 0.80 minus x, 0.20 minus x, and 2x. So we know, okay, so let's take a look at that. Okay, so now we're going to write out our expression for Kc. Kc is NO squared over the nitrogen concentration times the oxygen concentration. And this is going to be equal to 2x squared over 0.80 minus x 0.20 minus x. And all of this is equal to 1 times 10 to the negative 5th. Yes, I know I'm dropping off the trailing zeros just to keep things looking tidy, but I will go back and take them into account at the end. All right, we look at that and we go, Ew, that's a quadratic. However, you do not need to solve the quadratic if 100K is smaller than the starting concentration. So typically this means that K has to be much less than 1 times 10 to the negative fourth. Why? Well, if X is very, very small compared to 0.80, then we can essentially say that this concentration for the nitrogen is 0.80. We can make that assumption. So you make an approximation that X is insignificant compared to the starting concentrations. Then the subtracted X's can be omitted. So I've shown here, we've worked all through getting to this equation right here. And now we're going to be working with this. So I'm going to slide this to the top of the page, okay? We're going to make an approximation that X is insignificant compared to the starting concentrations. Then the subtracted X's can be omitted. So 1 times 10 to the negative fifth, this equation is going to become 4x squared. And now we get to say 0.80 times 0.20. Oh, that looks very doable. So that's 1 times 10 to the negative fifth. So now we solve for X and we get X equals 6.32 times 10 to the negative fourth, okay? Oh, yay, we solved for X, but remember, we are not done. So we're going to go back to that bottom part of the equilibrium table so that we can see it up there. So we have the nitrogen is going to be approximately equal. Now take a look at 0.80 minus X. The 6.32 times 10 to the negative fourth is really, really small. So really our nitrogen is 0.80 molar. Likewise, our oxygen is equal to 0.20 minus X, but we can say that this is 0.20 molar. Let's put a box around both of those. Now, when we're looking at the concentration of the nitrogen monoxide, that is equal to 2X. Okay, so now we have to actually use the X. So this is going to be equal to 2 times 6.32 times 10 to the negative fourth. And that is going to be equal to, I haven't actually solved for that. Let me do that very quickly. 2 times 6.32 second EE negative fourth. That is going to be 0.001264. Let's take a look at significant digits. Notice up here that I am limited to 2 significant digits. So my answer is going to be 0.0013 molar. So let's roll back and look at what we did. We ended up, when we worked through the Rice table, with this rather messy circled equation where we had 2x squared over 0.80 minus x times 0.20 minus x equals 1 times 10 to the negative fifth. And in your head you went, oh, I hate quadratics. Now, you can solve the quadratic if you want. Okay, you can put it into your calculator and that will be just fine. But on the AP exam, they are going to choose it in such a way that you can make the assumption safely. So when we make the assumption that X is small compared to the starting concentrations, then we see the drastic simplification where the X's become insignificant compared to the starting concentrations. And then it becomes an easily solvable problem. Now, one of the key things here is tell the grader that X is tiny compared to the starting materials, compared to starting concentrations. And so that will have the grader prepared to look at your work. A lot of students will actually solve these using the quadratic because they're comfortable doing that on their calculator, but there is absolutely no advantage to doing that. So you can use the assumption. All right, I think that's enough for the day.